All right, so here we have a heart. Let's do some labeling of it just so that we're clear on what part is what. This is the right atrium, and then below is the right ventricle. And this is the left. And those are the ventricles. Okay. So now what I'm going to do is, they always illustrated as being yellow, which I hate. So I'm going to do pink. No, it's probably not different enough. How about blue? So the question was just a request to go over the electrical events of the heart, specifically the EKG stuff, and how that translates to the waves you see on the EKG and what could cause something like tachycardia or other arrhythmias. So that's what I'm going to be addressing. But we're starting with the nodal system, which I'm going to draw now. So I've just drawn the SA node and the AV node. And now I'm drawing the bundle branches. And now I am drawing the Purkinje fibers. So I'll label these as well. Actually, you know what? I'll label them as I talk about them. How's that? All right, so in blue, we have the nodal system of the heart. So one thing that I want to stress, because this is why I did not illustrate the nodal system as being yellow, and I mentioned offhandedly that I didn't like that about your book. Here's why. Your book illustrates the gross anatomy of all nerves as being yellow. And then it does the same thing for the nodal system of the heart. It introduces the nodal system and it draws them in the exact same way that the illustrator draws nerves. The nodal system is not nervous tissue, though. The nodal system are just specialized, electrically different cardiac muscle cells. And so the fact that your book illustrates them as being yellow is misleading because it causes students to kind of just naturally draw the conclusion that, oh, those are yellow, they must be nerves. But they're absolutely not nerves. So it's one of the places in your book where you can very much tell that the person who made the figures was an illustrator first and an anatomist second. So I'm here to tell you that they are not nerves. All right. So in order to excite a muscle and cause it to generate tension, we must depolarize it. And this is a concept that you guys had all the way back in 241 with the introduction of the muscular system and the neuromuscular junction. Same deal here, because the heart is striated muscle. It's not skeletal muscle, but it is indeed striated. So the SA node, which I'm going to write out, sinoatrial node, fires first. And I want to stress, similarly to my sort of announcement about the nodal system not being nerves, the sinoatrial node has its own intrinsic rate of depolarization that is self-generated. So another thing students wonder about or sometimes mistakenly assume is that the sinoatrial node is controlled by the central nervous system, meaning your CNS initiates every heartbeat. That's not true. The SA node depolarizes by itself. It's only the speed of the SA node that is modulated by the central nervous system. So the sinoatrial node fires all by itself. And that excitation, which I'm going to represent in orange, spreads throughout the atrial myocardium and crosses the interatrial septum to spread to the other side as well.
That bit's just direct muscle kind of there through the intercalated discs, there's no Purkinje fibers that go from the right atrium to the left atrium.
Correct. There are no Purkinje fibers. It's just the intercalated discs. So quick review of intercalated discs, and thank you for bringing that up. Those were those pesky, faint little things that you had to look for in cardiac muscle. Students hate trying to find them, and I understand why. They're not super easy to find, especially on a real microscope. They are extra dense areas where cardiac muscle cells join to one another. And the reason that they are extra dense is because they have an abundance of two kinds of proteins. One is desmosome proteins for those desmosome cell junctions. And the other one is connexon proteins for gap junctions. And so through the gap junctions, they share cytoplasm with their neighboring cell, which means that electrical changes can be easily transmitted from one cell to its neighbor. All right. So one thing I need to include here is the fibrous skeleton. So the fibrous skeleton is all the way throughout the heart, meaning it's in between all of your cardiac muscle fibers, but it forms this very important barrier which I'm going to call the fibroskeleton electrical barrier. This ensures that the spread of excitation away from the SA node cannot prematurely go downstairs and excite the ventricles. The only way that excitation can spread from the atria to the ventricles is via this little chunk of nodal cells right here, and that's called the internodal pathway because it goes from the sinoatrial node to the atrioventricular node. So let's label that too. And then I'm going to erase right atrium because we know that by now, so I have room to label other things. Okay, so that's the atrioventricular node. And so the internodal pathway conducts the excitement to the atrioventricular node. The atrioventricular node also has a slower rate of depolarization compared with the SA node. So there's resistance imposed by the internodal pathway. And then the atrioventricular node also has lower ion permeability, which makes it a resistor too. And that slows down the signal. And what it does is it gives the atria enough time to depolarize and contract down into the ventricles before ventricular ejection occurs. So it imposes a slight pause. And that pause is really important for proper heart function because your heart is supposed to operate by squishing blood down into the ventricles from the atria. And then once the ventricles are filled, ejecting that blood upwards. So the sequence of events and them not overlapping is important. And the electrical system of the heart is designed to maintain that sort of space in time to give that pause. Okay, so once the signal has made it, so let's do internodal pathway is 2, atrioventricular node is 3. After that, we've got the atrioventricular node is going to spread excitement to another structure, which is just this little short branch right here. That's called the AV bundle. Sometimes also called the bundle of His, H-I-S. That's just the name of the person who found it. And then after that, it goes down into the bundle branches. There's two of them. I'm labeling both. And this is an important structural and heart timing function thing as well, is the electrical excitation does not immediately spread up here. It goes down the bundle branches. So traveling wave of depolarization going down here. So the interventricular septum depolarizes first, and then the signal turns around at the apex of the heart to spread up the Purkinje fibers. So let's do 4. Wow, that was not good. Let's try that again. 4. And then the Purkinje fibers are number 5. So this phenomenon where the impulse travels down the interventricular septum first and only then has this turnaround point right here, that is critical because so muscular contraction must follow depolarization. So they're not happening at the same time. Cell must depolarize before it can contract. So there's a short time gap. And so if the wave of contraction follows the wave of depolarization, that means that if the signal turns around at the apex and goes from the bottom up, the heart is also going to contract. The ventricles are going to contract from the bottom up. And that's the most efficient way to eject blood. It's like squeezing toothpaste out of a tube. So if you are using a toothpaste tube properly, that means that you're going to go from the bottom up to efficiently eject the toothpaste out of the tube. You're not just going to kind of caveman style squeeze the middle, because that's going to cause toothpaste to go both above your hand and below your hand. Not efficient. So literally the way the Purkinje fibers and bundle branches are arranged and how they turn around at the bottom of the heart is what causes the proper order of contraction. So the contraction of the ventricles from the apex towards the base, which squeezes blood up and out. So in anatomy and physiology, the anatomy component is, hey, here are all the parts. This is what their names are. And physiology is how those parts work. An overarching theme here is that the structure of stuff is what permits its function, and that's true here too. So the way that the nodal system in the lower heart is physically arranged causes the physiological consequence, which is contraction from the bottom up and efficient ejection of blood. So that's the steps of the nodal system. So we've got sinoatrial node, travel of the impulse through the internodal pathway to the AV node, where there is a short pause. Then impulses are carried through the AV bundle into the bundle branches, and those descend in the interventricular septum. They travel either through the moderator band, which I'll talk about momentarily, or down to the apex of the heart, at which point those impulses turn around and climb up the ventricles of the heart via the Purkinje fibers, effectively causing depolarization and ventricular ejection from apex towards the base. Now, I mentioned I would talk about the moderator band. The moderator band is a rope of muscle that connects the interventricular septum with the wall of the right ventricle. The moderator band's job because the wall of the right ventricle is so much thinner than the wall of the left, is to put some tension on this wall right here and kind of prevent overstretching and overfilling of the right ventricle, and help it to also contract at the same time as the left, because you want your two ventricles to be contracting in sync with one another. So I wish we were doing dissections, because the sheep hearts or the pig hearts, depending on which we get, typically have a really robust moderator band that you can easily see. It's usually not as apparent on our human cadavers, but this term you can see neither, because we can't meet in person, unfortunately. So you're just gonna have to take my word for it that it's there. Okay, so now let's pivot over to the EKG waves. So before I make this go in the trash, for understanding stuff where the order and the shape matters for the function, like in the cardiovascular system, I recommend you guys drawing out the process and the steps in the way that I just did. And if you're thinking like, there's no way I could possibly do that for memory, I don't expect you to do that for memory. Start by going through and copying the steps from your book, and then try to draw it from memory increasingly. If you get to the point where you can draw all the steps from memory and then you check the book and you get it right, that means that you're really, really well prepared for the exam, and you can expect to do well on that content. But it's a different, more active way to study that might not feel as comfortable as what you're used to, but will definitely be more effective. All right, EKG waves. Let's do the thing. All right, EKG or electrocardiogram. Now notice the abbreviation has a difference. So the English word is electro with a C. The abbreviation is EKG, electro with a K. And keeping in mind that this is being recorded, and so your voice might be used, does anybody know why the abbreviation is different? If you don't, that's okay, I'm just checking.
Is it German initially?
It is, yes, but it's for a specific reason as well. So typically, if you're ordering an EKG for somebody, let's say you're working in the emergency department and you're ordering the EKG, that tends to mean that something is fairly urgently wrong and you want to get the heart situation sussed out quickly. If you are a physician and you're yelling for an ECG and your nurse mishears EEG, which would be easy to do because ECG and EEG sound really similar, especially if you're in a loud environment. EEG is an electroencephalogram, which measures brain activity. And so what you don't want to have happen is that you need this urgent cardiovascular test, and then somebody brings the wrong instrumentation, and that costs you time, essentially, which can be fatal in certain contexts. So we don't want to do that. And so just to sort of aurally, AURALLY, disambiguate between EKG and ECG and EEG, we just use the German abbreviation instead, because EKG sounds very different. All right. So what I'm going to do right now is demonstrate a skill that I expect you to be able to do as well by the time the exam rolls around. So not yet, so don't feel intimidated, but eventually. So be able to draw one of those and be able to label it. And I'm actually going to draw another one trailing it because now notice my amplitudes are a little bit different. That doesn't really matter much here because if you look at an actual human EKG, the magnitudes also vary slightly sometimes. So the amplitude means the height of the curve. Alrighty, so that distance is the distance of one cardiac cycle. The reason we measure it from the QRS complex to QRS complex is typically because it's just the easiest and most obvious piece of the wave, right? And so for at rest, this is about 0.8 seconds. Or 800 milliseconds. So let's label our waves, which is easy because they go in alphabetical order. PQRST. So all right, so P is atrial depolarization. QRS represents ventricular depolarization, with the different parts, Q, R, and S, representing the steps on the way to ventricular depolarization. So traveling through the bundle of His, just here, and then depolarizing all of the Purkinje fibers all the way up. So that's the reason for that. But the QRS complex can really be condensed into the events of ventricular depolarization. And then we have ventricular repolarization, so re, not D, in the T wave. So you might notice that something is missing from this wave set if you look at the way I've labeled them. What is missing?
Atrial repolarization.
Yes, bingo. So does that mean that atrial repolarization doesn't happen? No, it has to. It's just hidden or masked by the QRS complex. So that the electrical magnitude of the QRS complex is so large that it swamps out and sort of hides the atrial repolarization. I also want to stress that this specific pattern that you're seeing here, this is a 12 lead EKG with classic lead placement. So 12 leads means there are 6 pairs of electrodes. Within each pair of electrodes, there is a cathode and an anode. So the cathode is the one from which electrons are flowing, and the anode is the one towards which electrodes are going. So they have a directional, they have an electrical direction. And then you put the pairs of leads on opposite sides of the heart from each other on the skin so that they can measure the flux of ions from one lead to another. And fortunately, since skin is conductive, we can measure this non-invasively, which is a pretty neat trick. So the reason I'm stressing this is because you can change the lead placement to look at different things about the heart. So you can put leads in different places to, for example, reveal atrial repolarization if you want to, or examine other things, because really each pair of leads is one camera angle looking through the heart. Which brings me to another phenomenon that I need to stress. And that is, think back to when you were learning action potentials. Remember that? Probably a scary time in your life because that's kind of right around the time that 241 starts to get really difficult, where you're cruising along learning about skin and tissues and you're like, all right, this is chill. And then suddenly you have to learn action potentials and that's far less chill. So in action potential land, up equals depolarization. And in action potential land, down equals repolarization. So because of those things, which is true for action potential graphical representation, students tend to assume that the EKG wave pattern is the exact same thing. It's not. Because over here, we've got T wave, and it's going up, but it's repolarization, not depolarization. So the whole up equals depolarization and down equals repolarization thing does not hold for the EKG wave trace. And that's because it's not measured the same way as an action potential is measured. An action potential is measured by measuring the electrical activity inside of a single cell, so a neuron or a muscle cell. The EKG is looking at electrical patterns across an entire heart, which is a huge population of cells. So although both an action potential diagram and an EKG wave are measuring electrical activity, they're doing that at two different scales, which means that you cannot make the same assumptions about the waveforms. Alrighty, so let's talk about what might disrupt these, because that was also part of the question. And unfortunately, I'm gonna have to be really vague about that because the causes for cardiac arrhythmias are myriad. There's lots of them, and they depend on a lot of different things. So let's take, for example, this 0.8 seconds. So the example that you gave in the question was what could cause a tachycardia, for example. So I'm going to erase this and I'm going to draw what tachycardia would look like.
If it makes the explanation easier, we could be more specific and say a supraventricular tachycardia.
So for SVTs, that might be diving in a bit too much for people who haven't read chapter 20 yet. So let me start with regular tachycardia and then I'll move from there into SVT, I think. So, because those are interesting, especially if they devolve into the phenomenon of torsades de pointes, which is my favorite tachycardia, or my favorite arrhythmia. Yes, I have a favorite one, but you know, depending on what the etiology is, that can look different. So let's start with a regular old one. All right, so let's just say, I'm going to draw a couple of these in a row. This one is normal. So we're assuming that the sinus rhythm, another way to say normal for this stuff is sinus rhythm. And so we're going to assume that there's no weird wave shapes. They're all pretty much nominal and that this distance is about 0.8 seconds. And we see all of the waves we're supposed to see. So nothing's missing, nothing's extra big, nothing's extra small. So that looks good. So I'm going to draw these a little bit more precisely than what you would see on an actual EKG readout because tachycardia starts to get messy looking when waves kind of all crash into each other. But so we see these waves are much closer together. So this is tachycardia. So with regard to what can cause tachycardia, now I want to stress tachycardia just means fast heart rate. And there are contexts in which you would expect to see this, right? So for example, if you decide that you're going to go for a run, you would expect your heart rate to increase to keep up with your physiological exercise demands. So when tachycardia starts to be a problem is when it's happening at rest. So a bunch of different things can cause this. Common ones are electrolyte imbalance. So if you have your heart cells to depolarize and contract, rely extra heavily on extracellular calcium. Your cardiac muscle cells don't have much of a sarcoplasmic reticulum, so they have a more heavy reliance on extracellular calcium, which means that if you have calcium dysregulation in your body fluids, it starts to affect the heart very quickly. So that's one possibility. Also, potassium changes, so extracellular potassium increase can cause tachycardia as well, just because it changes the membrane potential and makes the membranes easier to excite. So that's one. Drugs, sometimes of abuse. So amphetamines, cocaine, these can cause dangerous tachycardias that can kill you, which is why, you know, shouldn't do those. But also drugs not of abuse. So for example, Ritalin or dextroamphetamine, which is another name for Adderall. Those are prescribed drugs, and when used as prescribed, one side effect is some degree of tachycardia because they are stimulants, but as long as they're taken as directed, they shouldn't cause life-threatening tachycardias.
Can I ask a quick question on that?
Absolutely.
So if, and this is kind of off subject probably a little bit, but
That's
my son takes those, so I'm just curious if you have like a chemical imbalance to where that's a necessary medication for you to function properly, is it still doing that to your heart, or is it slowing it down?
It's still doing that to your heart a little bit. Part of the dosage guidelines for those drugs are sort of a balancing act between a pharmacological dose that's going to be effective for the patient and manage the symptoms of whatever they're experiencing. So I'm assuming ADHD, something of that flavor, but not so much that it's causing heart rate changes that are going to be unhealthy in the long term.
Okay, makes sense.
And one of the challenges for that is that specifically with dextroamphetamine is that patients develop a tolerance for it, just like other drugs, which means that it's less effective over time. So the dose requirement is higher, and that's where you can kind of get into the danger zone.
Yeah.
Which is challenging. It sucks that like something that's, you know, kind of a precarious drug that can, you know, can be harmful and can be abused is also, you know, so helpful to people that are, you know, dealing with imbalances that cause attention problems.
Right.
So that is tachycardia. And now, so now that we've introduced that idea that tachycardia is sort of essentially just faster than normal heart rate while at rest, let's talk about supraventricular tachycardia. And to do that, I'm going to erase some stuff and kind of break it down. And I'm going to have to draw a little bit of a explainer next to it. So let me. So as far as looking at an EKG, there's a zone of overlap where it's pretty much impossible to tell the difference between a supraventricular tachycardia and a regular one. And that is because of the supraventricular portion of the tachycardia. So let's draw that, and I'm going to do some term disambiguation as well. So SVT, or supraventricular tachycardia, describes two things. The tachycardia portion of the word describes the heart speed, so too fast, and the supraventricular part of the terminology refers specifically to what part of the heart is malfunctioning to cause that. And for this, I unfortunately need to real fast draw my heart diagram again. So just give me a second. It's probably going to look messy. I apologize in advance. All right, let me give myself a nodal system. Once again, not in yellow. Alrighty, so this goes back to my point I was making earlier about how the impulse is supposed to go directionally down the interventricular septum and then up after it turns around at the base. What it's not supposed to do is excite the top part of the ventricle first. But in a supraventricular tachycardia, that is what it does. So what you get is called a re-entrant rhythm. Where you get this little feedback loop between usually the AV node or the first part of the bundle branches, where it accidentally excites the top part first. So instead of going this way, like it's supposed to, the neighboring areas of the top part of the ventricles are excited. And because the impulse is not taking the time to spread down the interventricular septum and then turn around at the apex, we get two problems. One is that the ventricles are excited and contract too early. And two, the re-entrant portion is when the too early excitation feeds back onto the nodal system, creating a positive feedback loop. So this is where we get into the electrical stuff, the difference between the action potential waveform of the contractile cells and the nodal cells. But to sort of summarize, but in both cases, there's a refractory period during which it's impossible to re-excite or very, very difficult to re-excite the same set of cells. And with a re-entrant rhythm, there's basically a mistiming such that the neighboring contractile cells are able to get around the refractory period of the nodal cells and refire the nodal cells, because everything, of course, is connected by intercalated discs with not desmosomes, but gap junctions. And so it creates this little positive feedback loop, which means the ventricles are doing their thing a lot more frequently. So I mentioned previously that there was let me label my EKG here. This is regular flavor tachycardia. So if I have an SA node that's functioning normally, but a supraventricular tachycardia that is a re-entrant rhythm that keeps reactivating the ventricles, I might see something like this, where we have P, QRST, and then another QRS fluctuation, then another QRS fluctuation before I get another T wave. And then we have QRS, 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 T. So you can see that there's QRS complexes in weird little clusters where there shouldn't be, because there should be a P wave and a T wave on either side of every R peak. But if there's not, that means the ventricles are firing between the atria doing their thing normally.
So it's the absence of the P wave that's the key identifier there, because the ventricles are continuing to contract based on positive feedback loop without resetting the SA loop.
Exactly. Yeah. So if you were to look closely, you would see P and then R, R, R. There's another P, R, R, R. There's another P. And the reason I'm focusing on the R and the P waves is because when you're trying to identify arrhythmias visually, which any skilled emergency clinician should be able to do, you're not taking the time typically to be like, there's a slight ST elevation. You're just eyeballing the screen rapidly and looking for large themes in arrhythmia. So this would be SVT. And then let me do one more thing. So typically when you get this re-entrant rhythm thing going, when you have an SVT, they don't usually correct themselves. They actually tend to get worse until you enter VFib, which is ventricular fibrillation. And that's again because we have this positive feedback loop that's creating problems. So sometimes what you'll see before that is a phenomenon called torsades de points, which means twisting of the points. And this is right on the cusp. So you go from SVT to torsades de points, and then from torsades often to ventricular fibrillation. And that is where you have this strange pattern where you get a very diminished P wave, if any, and you get these increasing in magnitude, looking more like that, increasing in magnitude QRS complexes. And if you were to visually look at that, it looks like if you were to twist up a party streamer, where you have something that's going like this. Right? That's what torsades de points refers to, is it's the twisting of the points into this very specific waveform. And this is where you're getting in trouble, because the problem with SVTs at all, and tachycardia in general, is if your ventricles are going rogue and beating too soon, they don't have time to fill with blood before they're ejecting, which means that your cardiac output, so the amount of blood leaving your heart with each cycle, just tanks. It goes down really far. So let's say both tachycardia and SVTs and torsades all cause decrease cardiac output, and decreases in cardiac output are by definition dangerous, and you want to avoid those. All right, so I'm going to stop recording now because that recording went longer than I anticipated. That's fine.
Will you post the recordings to, or?
I have been, yeah.
Okay.
There's a separate playlist on YouTube that is specifically for these.
The short video.